Hello everyone, very good evening and welcome to the BYJU'S exam prep, the most comprehensive app for all competitive exams. I'm going to start monsoon series with what analog. Now here we will discuss what MOSFET biasing and stabilization. And guys, as you know, this topic is important for all competitive exams and this is also important for electrical and electronics student. Okay, let me know that everything is fine, sound quality, picture quality, everything is fine guys. Yes, please. Now please join the session now. Okay. 1 minute, give me 1 minute only. Okay. Now I think sound is perfect. Hello. Is it not audible? Okay then. Guys, in this series, we will discuss MOSFET biasing and stabilization, and then diode circuit, then finally BJT that is BJT biasing and stabilization, and fourth one is the application of operational amplifier. Okay, then this is my introduction. Myself Sanjay Rathi. I am having around 22 years of teaching experience, and guys remember, get the idea about the MOSFET. Okay, because this is important topic, and how to solve the question based on biasing, as well as what is the role of negative feedback, how we can make the Q point stabilize when we are giving the proper negative feedback. Now I will check, and then this is the in-depth preparation strategy for GATE 2024 by Dheeraj Sardana sir. Live interactive workshop. Please note the date on this Sunday, that is the 25th July at 7:30 p.m. tomorrow. That is on what? Tuesday. Okay. Then guys, now MOSFET biasing. What is the MOSFET biasing and then what? Stabilization guys. Right. I am going to discuss this. Biasing means what? How we can set the Q point. Right. Now this is MOSFET. This is gate terminal and this is source terminal. Okay. Normally we are taking the output from drain. Source is common, that's why it's called common source, and we are giving input toward gate terminal. Okay. Then that is what you have to set the Q point. Where is the Q point? Then go through the characteristics of the MOSFET. First of all, in saturation region, what is ID? ID is given by half of K and S W by L VGS minus VT the whole square. Right, where K and S is mu n COX, and W by L is the aspect ratio. Okay. Then guys, what is the meaning of biasing? Means what is the value of VGS? Because that current is controlled by what? VGS. Then what these characteristics? This is ID versus VGS. Okay. Now, suppose you are setting the VGS at this point. Now, Now you can find the value of ID here. And that is called IDQ. And we are setting the, this is called VGSQ. Okay, and this is the threshold voltage VT. Means VGS is greater than VT, and we are setting the value of VGSQ so that there we are getting the current VDQ. Okay, now we have to get the constant value of the slope here. Now watch this. This is a non-linear curve. This is a non-linear curve. What the small portion from this point to this point? From this point to this point, you can assume it was linear. You can assume it was linear from this point to this point, guys. Now, when we are changing the voltage, this is the VGSQ, that is the DC voltage. And when we are applying the VGS, that is the small voltage, then when the VGS will change, it will change the value of what? ID. This is what, from this point to this point, that is called ID. That is the change in ID because of change in what? VGS. And this point is called what? Q point. This point is called what? Q point. Okay. So we are setting the Q point in the middle of what? Saturation region. Okay. So that is the first characteristics. We have to set the point here so that the slope is very steep. Why we want that slope should be high? Because when there is a small change in VGS, there is a large change in what? ID. Now, and at the same time we have to maintain the linearity. Therefore, the change in the change in the VGS should be as small as possible, so that we can assume from this portion to this portion it will maintain a linearity. Because when we are going to apply, when we want to find a gain, then linear model means this is the linear model, GMVGS, and here we are using the RD, that is called small signal model. This is called what? Small signal model. This is the G terminal, this is S, and this voltage is VGS. And that is the source terminal. This is the drain terminal. Now, this is called small signal model, and that is what? Linear model. Now, we can use this model when we are setting the Q point here and the variation in the input is very, very small. And that's why the biasing is required. So, this is the first case why the biasing is required. Now, if suppose you want to set the Q point here, and for example, this is the circuit. Now, if there is a fault in this transistor, right? If there is some fault in this transistor, then we have to replace this transistor. Everything will remain same, VDD will remain same, RD will remain same, but there is a problem in what? This MOSFET. Then we will change this MOSFET. Once the MOSFET will change, what will happen? The characteristics will change. Then characteristics will change, guys. Then what will happen? Suppose you have set the VGSQ at this point, and what is the value of the IDQ? That is the case. But if the characteristics will change, what is the new characteristics then? Watch this. That this is the new character. This is for MOSFET number 1. This is the for MOSFET number 2. Now we are having the same value of the VGSQ. What is the current, guys? Very small. Current will change from this point to this point. Why this will change? Because the characteristics will change. Already we have replaced the MOSFET, and because of replacement of the MOSFET, the Q point will shift from this point to what? This point. From this point to this point, and that is the effect of what? Characteristics. Now, if you want to make it Q point independent of the properties of or internal parameter of the MOSFET, then we have to apply the negative feedback. Then, so which type of biasing I am going to use here? Then I will explain you. First of all, biasing by fixing the value of VGS. This is the first case already I have given. We have to fix this VGS. So there are different ways to fix this VGS. First way, take MOSFET here. and directly you can connect a battery here. VGG, like this is of 2-volt battery. This is the RG. This is in the range of mega ohm, RD, and this is the VD. Very simple biasing. Remember guys, the input resistance is infinite. That's why the IG is equal to 0. Then in that case, what is the VGS will become? Then VGS will become directly VGG. Directly DC voltage VGS. And now you can find the ID. Already I have given you the formula. From this formula you can find the ID. That is called what? Fixed biasing. But what is the problem in this circuit? We are having the two batteries. One is what? VDD here. One is what? VGG here. So there are two batteries, right? And now we have to use single battery. Then we have to use the single battery. Then what we can do? We can do what? Potential divider biasing. What is the potential divider biasing? Now, we are using the potential divider biasing here. This is R1, this is R2, this is VDD, and this is RD. Remember, these resistors are in the range of what? Mega ohm in case of MOSFET. Now this is RD, R1 and R2. Then you can apply the Thevenin's to solve this. If this is the question, how we can find the VGS? Cut it and then find the VGS. This is R1, this is R2, this is VDD. Now this is connected to G. Then what is the voltage at this point? This is nothing but VGS or VTH. R2 upon R1 plus R2 into VDD. Right? And then guys, remember, no need to find the RTH, because what is the input resistance of the MOSFET? Infinite. Suppose you are solving the RTH, then these R1 and R2 are in parallel. You can also find RTH, no problem. But there is no use of R1 parallel with R2, because input resistance of the MOSFET is infinite. This is VTH. That is VTH is equal to, why I am saying VTH is equal to VTH? Because this RTH, what is the current through this RTH? 0. And then this VTH will become VGS. Once you are able to find the VTH, then you can find the VGS, and from this equation again you can find the current. Again you can find the current, and MOSFET is in what? Saturation. Okay, for MOSFET to be in saturation region. Now, okay, Pramit Banerjee, congratulations. How are you? Now, guys, about placement, we will provide you the data for that. Okay. Now, so that is called what? One way fixing the VGT. Directly you can apply the battery, or single battery and you have to use the potentiometer. But already I have given now what is the problem here? Problem means if there is a problem in the MOSFET, and if you are changing the MOSFET, then it will create problem, guys. For example, M1, and we are replacing the M1 by what? M2. And there is a change in the characteristics. And because of that, for same value of VGS, the current will shift from ID1 to what? ID2, and so on. That is the problem. Okay. Now, to remove this problem, we are connecting what? RS. We are connecting RS to provide what? Negative feedback. And that is called, we are applying the RS for the stabilization of the circuit, guys. So biasing by fixing the VGS first case, and then biasing by fixing the VG and connecting a resistance in the source. Watch this. Here we are connecting the RS. Then what is the role of the RS here? Now, how we can find? This RS will provide a negative feedback here. Then if any numerical, if potential divider is given, this is the potential divider, R1, R2, this is RD, this is VDD, this is ID. Then first of all, find the Thevenin's equivalent. This is VTH, this is RTH, IG0, this is ID, this is RD, this is VDD, and that is ID. Now there is a drop, ID into RS. This is VGS. Now you have to apply the KVL in this loop. When we are applying the KVL in this loop, you will get VTH is equal to VGS plus ID into RS. What is the VGS? VTH minus ID into RS. But we are not having the value of the ID. Then you have to use the second equation. What is the ID in saturation region? Half of K and S W by L VGS minus VT the whole square. That is the value. From this equation and that equation, you can find the value of VGS and you can find the value of IDS. Okay. Now, what is the role of this RS? Okay. Because of these RS, right, there will be negative feedback. And when there is a change in the characteristics, then because of this negative feedback, we can maintain what? Q point, right? We can stabilize the Q point here, right? Now there is this is called one type of biasing where we are connecting the RS. If that will be the question, first of all apply the potential divider, then get the one equation from this loop, and then the second equation. By using these two equations, you can find the two values VGS and what ID. This is the method. Okay. Any other question, guys, related to that? If you have any question, then you can ask. Then next important thing is what? Biasing using a drain to gate feedback resistor. Watch this. Here we are connecting a resistor between drain and gate. That is called drain to gate or feedback resistor, and this is the question. Now, if that again, it will provide you negative feedback and the Q point is stable in this circuit. Then in how we can solve this type of numerical? Then remember, the current in this branch is 0. If the current in this branch is 0, in this case VDS is equal to what? VGS. VDS and VGS are equal. Then what is the condition for the saturation? VDS should be greater than VGS minus VT. That is confirmed here. That's why this type of circuit is always in what? Saturation region. Saturation region. And in saturation region, you can directly write one equation. ID is equal to half of K and S W by L VGS minus VT the whole square. Then second, VDD, right? We can write the KVL from this point to this point. What is the current here? 0. And VDS is equal to VGS. So what is the second equation here? ID is equal to what? VDD. This is the VDD minus VDS. And what is the VDS? VDS is nothing but VGS. VDD minus VGS upon RD. Okay. Again, we are having the two equations and two unknowns. From that, you can find the VGS and what? IDS. So that is another type of biasing. Very good evening. How are you, Chinmay? Then that is the second case. So biasing using the drain to gate feedback resistor. Okay. Now, so already I have discussed potential divider type biasing. Then we have connect the RS, and then that is what? Drain to gate feedback resistor. Now, there is one question that, can we directly connect RS here? This is RS and this is resistor is connected here. In case of enhancement MOSFET, remember, if you are connecting the RS without any battery, this is called cell biasing. And remember, in case of cell biasing, when we are writing the KVL from this point to this point, it will become VGS plus ID into RS is equal to 0. Why? Because what is the current through the RG? 0. You will get the VGS is equal to minus ID into RS. Minus ID into RS, and that is what negative value. Remember, in case of N-channel MOSFET, VGS should be greater than VT. What is the VT? 1 volt. It should be positive. And here we are getting the negative value. If suppose VGS is negative, means what? It is in cutoff. It is in what? Cutoff. The circuit will not work, guys. So that is the case. Okay. Venkat Ram, sir, once. That is a part of what digital. I will cover it in digital. What is the CMOS circuit and how we are going to design the memory and how we are going to solve the question, transmission gate and so on. Right? This is a part of what analog where we have to deal the which type of biasing we are going to use. Now, so these are the 3 cases. So new students, please watch that. First of all, that is the potential divider biasing, right? Then simply apply the Thevenin's theorem, get the answer with the RS, and then guys, already I have given this one, drain to gate feedback resistor, and in third type we are having what? Direct a current source here. At this point you will get a current source, 1 milliampere or 1 ampere and something like that. Then in that case it will directly give you the value of the ID, right? This is the ID and IS, this is the source current or drain current. So that is what? Direct a current source it is given. This current source is nothing but what? Current mirror circuit. Okay, current mirror circuit. So it is, we are connecting here. If in any numerical, if the value of that ID is given, means it is the value, directly you can use this value. So now, so we have discussed, now we are going to solve some numericals on this. What are the numericals? First one, okay, tell me. Consider the following circuit. Process transconductance parameter is 0.50 milliampere per volt. Process transconductance parameter means what? K and S. Mu n COX. K and S is nothing but mu n COX, that is given as 0.50 milliampere per volt square. Aspect ratio W by L is given as 1. Threshold voltage is given as 3 volt, that is too high, and VDD is 20 volt. Find the operating point of the circuit. When operating point is asked, means guys, you have to calculate, first of all calculate the current, and then we can calculate the operating point here. Okay. Now, in this case, we have to apply what? Thevenin's equation. So then find the Thevenin's. Okay. Then tell me. This is 35K, this is 20K. First of all, find the VTH. Okay, and then this is the VTH, 20 upon 20 plus 35 into 35. RS is connected here. This is 3 kilo ohm. Now, no need to find the RTH. This 5 kilo ohm is connected here, guys. Okay. Then apply the KCL. Already I have given ID. Then consider the following circuit. Process transconductor parameter is given. Find the operating point of the circuit. Now how we can find the current? Then in that case, first of all, you have to assume that the transistor is in what? Saturation region. If you are assuming the transistor is in saturation region, then you can use the, first of all, find that formula. Then you can use what? IDS is equal to, second formula, half of K and S W by L VGS minus VT the whole square. Okay. What is the value here? Half of K and S is given 0.5 into 1, that is in milliampere. VGS, you have to find the VGS. VT is given as 3 the whole square. That is one equation. That is the relation between IDS and VDS. First one. Second, what is the VGS ID? From that already I have given you the formula. VGS will become VTH minus ID into what? 5 kilo ohm. ID into what? 5 kilo ohm. And VTH, you can find the VTH from that. And then put this value of the VGS in this equation. You will get the quadratic equation and then solve it. Then you can solve these values, guys. Okay. So that is the one way to solve this question. Yes, Chinmay, what you want to say? Okay then. IDS 1 by 2. Yes. That is the formula. Now these are the two equations. Try to solve. Get the answer and give me the answer in my comments box, guys. Now ultimately you have to check once, because it is not in cutoff, it may be in what? Triode region, or it may be in what? Saturation region. Triode means if you are assuming that it is in what? Saturation, because when we are using this formula, we are assuming it is in saturation. When it is in saturation, or you can verify from the diagram also, right? Once we are applying the voltage and that RD is connected, then find the VDS and it should be greater than what? VGS minus VT. If it is greater than VGS minus VT, then it is in saturation region. And if the VDS is less than VGS minus VT, then guys it is in what? Triode region. And for triode region, what is the IDS? K and S W by L VGS minus VT into what? VDS minus half of VDS square. You can use this formula in that case if it is not in saturation. Okay. Okay then, this value, this is the value, half of K and S W by L VGS minus VT the whole square, and this is the value. Now try to solve with this two formula. Then 1 minute. Now sometimes we are getting this type of questions where the current source is given. In MOSFET, that current source is given to the source terminal. Already I have given, this is a current mirror circuit. Now the transistor in the given circuit has VT threshold voltage 0.5 volt, Kn or Kp 20 milliampere per volt square, and lambda is equal to 0. When the lambda is 0 means what? We have to neglect the channel length modulation. That is called early effect. Neglect the channel length modulation. I is equal to 0.9 milliampere. This is the I, 0.9 milliampere. Assume that the minimum voltage VCS required across each current source is 0.3 volt. Okay. V0 as a function of Vi, assuming the transistor are operating in saturation. Already we have assumed that is in the transistor, it is in saturation. Then what is asked here? What is this? Which one is correct here? Which one is correct here? Now assume that the minimum voltage VCS required across each transistor source is 0.3 volt. This is the 0.3 volt voltage we are having across that, right? And then this voltage is minus 2.5 voltage. 0.3 voltage is here. Then what is the value of the VGS? Then tell me. Just please everyone try to solve this question. Take your time and give me the answer. You have to find the value of the VGS here. VGS. What is the answer? Then in that case, because it is given in saturation, you can use this formula, right? K and S, it is given, right? Then this is if W by L it is not given, it is included in that. This is the complete value of this K and S W by L, that is in terms of what Kn 20 milliampere per volt square. You have to find the VGS. I is given, what is I? 0.9 milliampere, because 0.9 milliampere will flow like this. This is the current source and that current will pass through that, and from that you can find the value of VGS. Then Vi minus VGS will give you the V0. VGS. And remember, and what is the threshold that is given? Minimum voltage VCS required across each current source is what? 0.3 milliampere. Now try to solve this question. Okay, and guys, give me the answer in my comments box. Now tomorrow we have session on what? Diode circuit. And after that, biasing and stabilization of BJT. Biasing and stabilization of BJT. And then after that, operational amplifier and inverting, everything about the inverting and non-inverting operational amplifier. Means what? What is inverting and non-inverting operational amplifier? What is inverting summer, non-inverting summer? How we are going to design what differential amplifier by using inverting and non-inverting terminals, right? And voltage to current converter, current to voltage converter. So that is based on what? Inverting and non-inverting operational amplifier. How to find the current in any branch, right? So this type of questions we are going to discuss in what? Operational amplifier and its application. Okay guys, you are try to give me the answer in my comments box. I already have given which type of biasing, and try to solve these 3 questions and give me the answer in comments box or on my Telegram channel. Okay guys, then thank you for attending the session. You are on BYJU'S exam prep. Subscribe the channel, like the session and share the link of this session. Thank you and good night.